Hello. I'm going to demonstrate how to do a very nice trick with the purrr package in Tidyverse when you're dealing with EdgeR data. So the idea is to perform the EdgeR analysis with multiple contrasts and to store the result of all this in a single table. A single table which has all the information, the name of the gene, the log FC, the log CPM, the FDR, but also the name of the contrast. So instead of having multiple tables, one for each contrast, this analysis will end with just one. And to simplify the demonstration a little bit, I have started by creating the raw tables that I'm going to use. So first of all, we have a counts table which contains the three minimum columns. NGI ID here is the ID for the sample. Feature is the identifier for the gene, and count is the count for that gene in that sample. On top of that, I'm not sure if we're actually going to use it. Yeah, well, we are going to use it. We have a table of samples. This contains also the NGI ID, common identifier here. It contains also the three factors involved in this particular experiment: the bacterial strain used, the food source used, combined or actually made from two different factors, the phytoplankton species and the growth phase. In addition to that, we have replicate numbers here and a joint identifier for the three factors, which will be used when we create the design matrix. And I think, yes, this is up here. This is relatively straightforward, but I'm going to show you how I do a data frame that does, well, the EdgeR samples is a table which can't have row names, but when you call the model matrix, you need to have row names. So I just want to point out this function if you didn't know about it so far. It's in the table package, column to row names. So we can run this. And you note here the TRG, that was the constructed joint identifier for the three factors. So if we then look in the design matrix, this will be familiar to you. It has the sample, the treatment identifier here, and all the samples. And then you have a number for whether this particular sample belongs to that group or not. Straightforward. So we close that. From this, we can now create an EdgeR object. And usually you probably do that by multiple assignments. So you do it one step at a time, creating new variables or maybe possibly overwriting variables as you go. With this, I'm going to show you how you can chain all this in a long pipeline instead. And I will run it step by step so that you follow. The first thing is very easy, is essentially just selecting all the columns from the table, the counts table. So the select is actually not needed anymore. I had another structure before. So this is just a counts table when we run the first line. The next two lines here are going to filter away features or genes that have a count that is lower than this value, the feature min count, which is in my case is set to 5. You can see that over here. So this is instead of using the row sum function. What it does is that it groups by feature, which is expected. So you take a sum of the counts over all the features. But instead of using the summarize function, I'm using mutate, so I'm adding a new column called feet total to each row. So we can run that and have a look at what it looks like. Here. And here you can see the feet total. If we order this on feature instead, well, this feature had a feature total of 0, but as you can see, this feature here has different counts, but it has all the same number for feature total. Meaning that we can use this column then in the next step to filter those that do not have a total of larger than 5 over all the samples, considering them as noise. So this is what this step does. It essentially just filters using the constant I have already defined here of 5, and then it drops that column because it's just going to hinder us in the next step. We can run that and you can see that we will lose the first feature, then the one that had a 0. As you can see, there is now a feature here which is called 10, which apparently has or clearly has a sum that is larger than 5 over all the samples. In the next step, we will spread this, taking the count, the NGI ID then as the new column header, and the count as the count in each. I will not run this because it will have so many columns, so it will not open properly in RStudio anyway, so we can't look at it. The next step here pipes the output from that to as data frame, which I showed before in this call here. This is to turn the tibble into a data frame, because tibbles cannot have row names and we need row names. And then I call this column to row names function from the tibble package again. Next, I pipe this to, so up to here, this is a normal data frame. But now I can pipe this to GGE list. And what you should remember is the way the pipe function, the pipe operator works, is that it will send in the output from this last function here into this function as the first argument. And the first argument here is the count matrix, which doesn't have to be strictly a matrix. It can be a data frame that looks like a matrix too. So we can run this part of the code. And now you see that the EdgeR object is no longer a data frame with the number of observations and variables, but instead a DGE list object like we expect. And here's what it looks like. We have all the counts, we have the samples here, and nothing special. It has calculated this library size and some normalization factors that are all set to 1 at this moment, because we haven't yet run the normalization code. This is actually the next step. So we just take the output from that and run the normalization factors, calculate normalization factors. We have a look at the output here, and under samples, okay, but let's see if it's refreshed. It's not always refreshed. Okay, so the normalization factors are still just ones. I don't know why. Anyway, in the last step then, we, in one single function call, one can now, this is a relatively new EdgeR function call, I think, which does common, trended, and tag-wise dispersion calculations in one single call. So by that we can run this entire block of code like this. So this is a very concise way of doing our analysis, but it's also very easy to follow because it's just one step at a time per line, basically. And if we then look at the EdgeR object, we actually need to close it because otherwise it won't refresh. That's what was wrong before. So now you can see that we have dispersion factors calculated here, and some other things, so the method used for the trended dispersion. Let's see now if we have normalization factors. Yeah, and as you can see now, the normalization factors are different from what they were before. So the problem with what I showed you before was that it wasn't refreshed, even though I opened it again. So let's close these things so we are sure that they actually refresh. The next step is pretty simple, but I can show you how to do a pipeline here too. I want to write the counts per million using the CPM function in EdgeR. So I get the estimated corrected counts per million from EdgeR with the CPM function, which just takes the object as its first argument or only argument. Here again, I don't think this is, or this is actually, I think this returns a numerical matrix. So therefore I need to call this as data frames. Row names to column, so we get the feature as a proper column instead of row names. And then I gather the resulting thing here to make it long instead of wide. I filter out those that have a count per million which is 0, so only keeping those that are higher than 0. And then I write the whole thing to this table here. I don't need to run it now because I ran it before. So on to the fitting. The fitting has no surprises. It just takes the EdgeR object and the design matrix and performs this glmql fit, which according to the current documentation is the fitting method to try first at least. So we run that. And now we come to the last step, which is testing some of the contrasts to see what significant genes we get, or actually what we get for fold change and log CPM for all genes, not only the significant, as you well know. I start by creating this contrasts matrix with the make contrast method from EdgeR. So we run that. We can have a look at that. This is a normal matrix where all the samples are both as columns, or all the treatments are found both as columns and as rows. So this means that this particular column here, these two treatments will be compared with that treatment. Now comes the real magic of what I'm going to show you tonight, because this is a pipeline then that does everything, starting from what we have here, the EdgeR object and the contrasts, and it performs all the tests on the different contrasts, and it retrieves the top tags, and then in the end it will write it to file. I will go stepwise here too. So we start by creating a table made up only of one column, a single column, with this contrasts. So we run that and see what that looks like. And here we have it. This is just a list of the contrasts we already defined up here. Got them from call names of that. Now, in the first step, we need to run a test to test this particular contrast on the fitted EdgeR object, and this is where the purrr map function comes in. This will, for each contrast in this, it will define a new column called test, in which the result of applying an individual contrast to this function here will be stored. So the first argument here is the variable we're working with, the contrast. The second argument is any function. So here I've defined my own function. I could have done this differently, but I needed this because the first argument to this particular function is not just a string with a contrast. I need to put in the EdgeR fit first, so therefore I do this function thing here. The second argument to glmqlf test is the contrast, and the contrast here is addressed with the name of the contrast as the indexing like this. So this will, for the first thing, it will extract this column. Second run, it will extract that column, and then that column, and that column, and so on. So let's run this and see what it looks like. Make this a little bit larger. See here that now we have a table consisting of 7 rows like before and 2 columns. The first column is a normal string column containing the contrasts, whereas the second is a list of GGELRT objects. So here inside the table we have the object that is the result of calling this function. This object will then be used in the next step here. The next step will take the DGELRT column, the test column, and it will apply the top tags function to that. As you can see, it's similar here. We use the map function, the test, to tell which other column to use here, and then apply this to top tags. Run that. And as you can see here, now we have 3 columns, DG, the string, the former one here, and now we have a top tags object. Now we want actually a table of top tags instead of the top tags objects. We could have extracted that immediately here because we're not actually going to use the top tags object in any way. We're just going to throw it away, but I did it this way anyway. So in the next step, the third step here, defining the fourth column, I will use the map function again, but now on the top tags object, or top tags list of top tags objects. And I will apply this new function here, taking a TT, a top tag object. And I will take that, extract the table, and turn row names into columns. So the feature, so we get back the feature column. We run that. Now, what we get in our result is actually a new column containing a data frame. So this is a table that it by itself contains data frames. Tables can also contain tables, of course, but this is a nested table then, because it's a sort of a data frame that contains data frames. Now, we're very close to what we actually want to achieve with this. What we want to do next is that we actually want to extract all the data from each of these data frames into those 6 columns and these rows here, and use and keep this one but expand it. So each of those 5,600 rows here should have a row with contrast here, or should have a column with contrast. And this is what an unnest function does. It unnests tables like this. And now, as you can see, it didn't unnest. We never had to actually specify the contrasts, because that's a list variable that is just easy. This is just a list of characters which is easy to extract. The other 2 does not get extracted in this unnesting because they can't really be unnested. And we specified this one to unnest that, the table thing here. And what we get is exactly what we wanted. It's a table containing almost 40,000 rows and 7 columns in the format we wanted it. So we have the contrast, we have the feature, log fold change, and then all the other variables we're used to in EdgeR. And in the last step then, which I'm not going to run here because it doesn't show well, I write the whole thing to a tab separated file. And once again then, the pipe operator here will pipe in the result of this, so the table that looks like this, as the first argument to write TSV. So that was it, and please contact me if you have questions or want the source code for the script. Bye for now.